Hello everyone, welcome to my channel. So today in this lecture, in this podcast, we are going to discuss about glycolysis and gluconeogenesis, glycogen metabolism. Okay, so let's begin. So let's talk about glycolysis. What is glycolysis? All the reactions of the glycolysis. Okay, and we are going to see the disorders of glycogen metabolism also. So let's begin. Very excited for the video podcast. Okay, let's see. So glycolysis is derived from the Greek word glucose means glycolysis is derived from the Greek word glucose means sweet or sugar, lysis means dissolution. So it is a universal pathway in living cells. The complete pathway of glycolysis was elucidated in 1940. So this pathway is often referred to as Embden-Meyerhoff-Parnas pathway, EMP pathway. Embden-Meyerhoff-Parnas pathway. In honor of the biochemist who made a major contributor to the knowledge of glycolysis. Actually, during the World Wars, Emden Meyerhoff and Parna, not this one, not this one. And that is C3C4 cycle I was talking about. No. So, Emden Meyerhoff and Parnas EMP pathway. So, major contribution of these biochemists. Okay, glycolysis is defined as a sequence of reactions converting glucose or glycogen to pyruvate or lactate with the production of ATP. So glycolysis is defined as the sequence of reactions converting glucose or glycogen to pyruvate or lactate with the production of ATP. Sequence of reactions converting glucose to lactate. Silent features. What are the silent features? Glycolysis takes place in all cells of the body. The enzyme of this pathway are present in the cytosol fraction of the cell. It is present in the cytoplasm. Glycolysis occurs in the absence of oxygen, hence it is anaerobic, or in the presence of oxygen, that is aerobic. Lactate is the end product under anaerobic conditions. In the aerobic conditions, pyruvate is formed, which is then oxidized to carbon dioxide and water. So glycolysis takes place in all cells of the body. The enzyme of this pathway are present in cytosomal fraction of the cell. Glycolysis occurs in the absence of oxygen, hence it is anaerobic, or in the presence of oxygen, aerobic. So lactate is the end product under aerobic conditions. Lactate is the end product. In the aerobic condition, pyruvate is formed, which is then oxidized to carbon dioxide and water. Okay, glycolysis is a major pathway for ATP synthesis in tissues lacking mitochondria. Example, your RBC, erythrocytes. In cornea also there is no mitochondria. In lens also there is no mitochondria. So ECL, erythrocyte, cornea and lens, they lack mitochondria, and hence glycolysis is the major pathway for them. ECL, erythrocyte, cornea and lens. So take home point is cornea and lens also lack a mitochondria. So ECL lack mitochondria, erythrocyte, cornea and lens. Take home point. Okay, glycolysis is very essential for brain, which is dependent on glucose for energy. Glycolysis is very essential for brain, which is dependent on glucose for energy. Also ketone bodies also utilized by brain, but the main is glucose. So glycolysis is very essential for brain. The glucose in brain has to undergo glycolysis before it is oxidized to carbon dioxide and water. It has to undergo glycolysis. Glycolysis anaerobic may be summarized by the net reaction glucose plus 2 ADP plus 2 inorganic phosphate will give you 2 lactate and 2 ATP. So anaerobic glycolysis will yield you 2 lactate and 2 ATP by utilizing 2 ADP and 2 inorganic phosphate and glucose. The glycolysis is a central metabolic pathway in many of its intermediate providing branching points to other pathways. And thus, the intermediate of glycolysis are useful for the synthesis of amino acids and fat. Acids and fats are synthesized from the intermediates of glycolysis. Reversal of glycolysis along with alternate arrangement at the irreversible step will result in synthesis of glucose. So, if you reverse the irreversible steps, it will result in the synthesis of glucose, that is called the gluconeogenesis. We are going to look in this video. So reactions of glycolysis in this podcast. Okay, so reactions of glycolysis. An overview of glycolysis is depicted. While detailed sequence of reactions is given, the pathway can be divided into 3 distinct phases: energy investment phase or priming stage, splitting phase, energy generation phase. So reactions of glycolysis is divide into three distinct phases. First is energy investment phase, or you can say priming stage, and the second one is the splitting phase, and the third one is energy generation phase. So we'll be understanding it. The sequences of reactions are discussed. Energy investment phase or preparatory phase. Glucose is phosphorylated to glucose 6-phosphate by hexokinase or glucokinase. So glucose is phosphorylated to glucose 6-phosphate by hexokinase or glucokinase. So the sequence of reactions are discussed. Energy investment phase. Energy investment phase, preparatory phase. It is a preparatory phase. Glucose is phosphorylated to glucose 6-phosphate by hexokinase or glucokinase. In energy investment phase, glucose is phosphorylated to glucose 6-phosphate by hexokinase or glucokinase. Both are isoenzymes. What are the difference in between them? We'll be looking at it. This is an irreversible reaction dependent on ATP and magnesium. Hexokinase means magnesium dependent and ATP dependent. ATP and magnesium. So take home point. Point to be noted. Point to be noted is hexokinase and glucokinase are isoenzymes and they require ATP and magnesium. The enzyme hexokinase is present in almost all the tissues. All the tissues hexokinase is present. All the tissues hexokinase. Hexo is for all hexoses. Okay, it catalyzes the phosphorylation of various hexoses, fructose, mannose, etc. It has a low Km for substrate, about 0.1 mm, and inhibited by glucose 6-phosphate. Low Km means less amount of the substrate is required to get the half the velocity. It has low Km and is inhibited by glucose 6-phosphate. So it is inhibited by glucose 6-phosphate. What is inhibited by glucose 6-phosphate? The hexokinase. Hexokinase is inhibited by glucose 6-phosphate. So glucose is phosphorylated to glucose 6-phosphate by hexokinase or glucokinase. Both are isoenzymes. It is ATP dependent and it is magnesium dependent, and it is irreversible reaction. So point to be noted, it is an irreversible reaction. So we have to reverse this for gluconeogenesis. Irreversible reaction. It is dependent on ATP and magnesium. Okay. 1 minute. Okay, so what is the difference between hexokinase and glucokinase? So point to be noted. So whatever points that must be there in your answer that you should remember at any cost is the dollar point. The dollar point I will be saying, and these points you need to remember and you have to put it into your answer, and you have to remember this all the time. Okay, always you have to remember always. Okay, so hexokinase and glucokinase, they are isoenzymes. So what is the difference between these isoenzymes? So both the enzymes are irreversible. Both the enzymes require ATP and magnesium. Now dollar point, that is what you have to definitely write in your answer. You should not miss this points. So what is the dollar point? Dollar point is hexokinase and glucokinase. What is the difference between them? The enzyme hexokinase is present in almost all the tissues. Dollar point, all the tissues. Glucokinase present in liver only. Glucokinase only in liver. Hexokinase all tissues. It catalyzes the phosphorylation of various hexoses, fructose, mannose, etc. Glucokinase phosphorylate only glucose. Glucokinase only GG, only glucose. Hexokinase all hexoses, fructose, mannose, etc. Hexokinase has low Km for substrate. Glucokinase has high Km for substrate. High Km. Hexokinase is inhibited by glucose 6-phosphate. Glucokinase is not inhibited by glucose 6-phosphate. So what are the differences? Hexokinase present in all tissues. It phosphorylates all hexoses, fructose, mannose, etc. It has low km. Hexokinase low km, and it is inhibited by glucose 6 phosphate. These 4 points you have to write. Okay. Glucokinase is present only in liver. It catalyzes phosphorylation of only glucose. It has high Km for glucose, and it is not inhibited by glucose 6 phosphate. High Km means low affinity. It has low affinity for glucose. Low affinity. Due to high affinity, low Km. Due to high affinity, glucokinase has low Km. Glucose is utilized by hexokinase even at low concentration. Hexokinase can utilize glucose even at low concentration. Actually, hexokinase is hungry for glucose. So at low concentration also, it will utilize it. Whereas glucokinase acts only at higher levels of glucose. That is, after a meal when blood glucose concentration is above 100 milligram per deciliter, then only glucokinase can utilize. Glucokinase is found in liver where glucose is abundant. Okay, so this thing you need to remember. These 5 points you need to remember. What are the dollar points? $5 points. Hexokinase, low Km, high affinity. High affinity means glucose is utilized even at low concentrations. Hexokinase phosphorylates all hexoses, fructose, mannose, etc. Hexokinase is inhibited by glucose 6 phosphate. Hexokinase is present in all tissues. It has low Km and high affinity. Glucokinase present in liver. It phosphorylates only glucose. It has high Km and low affinity, and it is inhibited by glucose 6 phosphate. Due to high affinity, low Km, glucose is utilized by hexokinase even at low concentrations. Whereas glucokinase acts only at a high levels of glucose, that is after a meal when blood glucose is above 100 milligram per deciliter. Okay, now talking about glucose 6 phosphate. So glucose 6 phosphate is impermeable to cell membrane. It is a central molecule with a variety of metabolic fates. So glucose 6 phosphate is impermeable to cell membrane. Cannot enter the cell membrane. So it is a central molecule with a variety of metabolic fates: glycolysis, glycogenesis, gluconeogenesis, pentose phosphate pathway. Glucose 6 phosphate undergoes isomerization to give fructose 6 phosphate in the presence of the enzyme phosphohexose. Phosphohexose isomerase, and magnesium. It is also magnesium dependent. So glucose 6 phosphate converts into fructose 6 phosphate. We require the enzyme isomerase. Isomerase to chahiye, but it is phosphohexose isomerase. Phospho means glucose 6 and fructose 6 phosphate. They contain phosphate to phospho, and both are hexoses. So phosphohexose isomerase. They convert the hexoses with 1 phosphates. Fructose 6 phosphate is phosphorylated to fructose 1,6 bisphosphate by phosphofructokinase. So it is adding 1 phosphate to fructokinase adding phosphate to phosphofructo. Already fructose is containing phosphate, and it is going to add ATP. So it is phosphofructokinase. This is an irreversible, committed, and a regulatory step in glycolysis. So this is irreversible and committed and a regulatory step in glycolysis. It is a regulatory step in glycolysis. Irreversible, committed, and a regulatory step. What is the regulatory step of phosphofructokinase? Is the regulatory enzyme and regulatory step fructose 6 phosphate to fructose 1,6 bisphosphate by phosphofructokinase 1. Okay, splitting phase. Talking about the splitting phase. So we have discussed energy investment phase. Let's talk about splitting phase. The 6 carbon fructose 1,6 bisphosphate is split, hence the name glycolysis. Splitting phase, it consists 6 carbon fructose 1,6 phosphate is split, hence the name glycolysis, by 2-3 carbon compounds. So the 6 carbon fructose 1,6-bisphosphate is split to two 3 carbon compounds, glyceraldehyde 3-phosphate and dihydroxyacetone phosphate, by the enzyme aldolase is what it's doing. It breaking down 6 carbon compound into 2 3 carbon compounds, that is glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Aldolase is also called fructose 1,6-bisphosphate aldolase means आधा कर रहा है, aldolase आधा कर रहा है. ओके, aldolase क्या कर रहा है, आधा कर रहा है. तो द 6 carbon fructose 1,6-bisphosphate is split has the name glycolysis. So it is split into 2 3 carbon compounds, glyceraldehyde 3-phosphate and dihydroxyacetone phosphate, by the enzyme aldolase, also called fructose 1,6-bisphosphate aldolase. The enzyme phosphotriose isomerase catalyzes the irreversible interconversion. It is the reversible interconversion of glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. The 2 molecules of glyceraldehyde 3-phosphate obtained from 1 molecule of glucose, you get 2 molecules of glyceraldehyde 3-phosphate. 2 molecules of glyceraldehyde 3-phosphate, you get from 1 molecule of glucose, you get 2G3P, glyceraldehyde 3-phosphate. So this is by phosphotriose isomerase. Both are containing 3 carbon atoms, so they are called phosphotriose isomerase, and both contain phosphate group. So phosphotriose isomerase. Previously we have discussed one isomerase. Can anyone tell which isomerase we discussed previously, just before this isomerase? We have discussed an enzyme and isomerase which converts glucose 6-phosphate to fructose 6-phosphate. Both contain phosphate and both are hexoses, so phosphohexose isomerase. This is phosphotriose isomerase. That was hexose, this is triose. This is phosphotriose and that was phosphohexose isomerase. Okay, now energy generation phase, that is payoff phase. Now it is paying off. So glyceraldehyde 3-phosphate dehydrogenase converts glyceraldehyde 3-phosphate to 1,3-phosphoglycerate. So G3P is converted into 1,3-bisphosphoglycerate, 1,3-BPG, bisphosphoglycerate, 1,3-bisphosphoglycerate. One more phosphate is added, so it is called glyceraldehyde 3-phosphate dehydrogenase. Dehydrogenase is the H plus. So this step is important as it is involved in the formation of NADH+. Dehydrogenase means it is losing its hydrogen. It's glyceraldehyde 3-phosphate losing its hydrogen and giving its hydrogen to NAD+ and forming NADH+. It's a high energy compound, 1,3-bisphosphoglycerate. 1,3-bisphosphoglycerate is a high energy compound. Okay, iodoacetate and arsenate inhibit the enzyme glyceraldehyde. MCQ. What glyceraldehyde 3-phosphate dehydrogenase को कौन करेगा? Inhibit. That is iodoacetate and arsenate. Iodoacetate and arsenate, they inhibit glyceraldehyde 3-phosphate dehydrogenase. Glyceraldehyde 3-phosphate dehydrogenase are inhibited by iodoacetate and arsenate. Iodoacetate and arsenate. Arsenate will inhibit. In aerobic condition, NADH passes through the electron transport chain and 5 ATP are synthesized by oxidative phosphorylation, because for one glyceraldehyde, one NADH+, H+ produced. So for 2 glyceraldehydes, because DAP is converted to glyceraldehyde 3-phosphate by phosphotriose phosphate, so this glyceraldehyde 3-phosphate, for one glyceraldehyde 3-phosphate you are getting 1 NADH+, H+. For 2 you will get 2 NADH+, H+, and for 2 into 2.5 ATP you will get 5 ATPs for 2 NADH+, H+ synthesized in the glycolysis by oxidative phosphorylation. So suppose we have reached till here. Now let's complete it. So the enzyme phosphoglycerate kinase acts on 1,3-bisphosphoglycerate, resulting in the synthesis of ATP and formation of 3-phosphoglycerate. The enzyme phosphoglycerate kinase acts on 1,3-bis phosphoglycerate. The enzyme phosphoglycerate kinase. Which enzyme? Phosphoglycerate kinase acts on 1,3-bis phosphoglycerate, resulting in the synthesis of ATP and formation of 3-phosphoglycerate. This step is a good example of substrate level phosphorylation. So this enzyme, the enzyme phosphoglycerate kinase, acts on 1,3-bis phosphoglycerate, resulting in the synthesis of ATP. So what is happening here is the enzyme phosphoglycerate kinase, it acts on 1,3-bis phosphoglycerate, resulting in the synthesis of ATP. So the enzyme phosphoglycerate kinase, so it is phosphoglycerate kinase, acts on 1,3-bis phosphoglycerate, resulting in the synthesis of ATP and formation of 3-phosphoglycerate. So you will get 3-phosphoglycerate by the enzyme phosphoglycerate kinase. Phosphoglycerate kinase. So you are going to remove 1 ATP from 1,3-bis phosphoglycerate and forming 3-phosphoglycerate. Going to remove. Okay, this step is a good example of substrate level phosphorylation, since ATP is synthesized from the substrate without the involvement of electron transport chain. So what is substrate level? Means without involvement of ETC. Without involvement of ETC is called substrate level phosphorylation. Phosphoglycerate kinase reaction is reversible. A rare example among the kinase reactions. So phosphoglycerate kinase is reversible. It is reversible enzyme. So till now we talked about what are irreversible, that is hexokinase or glucokinase, and phosphofructokinase. One is irreversible, others are reversible. So 3-phosphoglycerate is converted to phosphoglycerate by phosphoglycerate mutase. What is the work of mutase to convert phosphoglycerate mutase? We talked about phosphoglycerate kinase, now phosphoglycerate mutase, which mutes 3 to 2. It is also a reversible enzyme. This is an isomerization reaction. The high energy compound phosphoenol pyruvate is generated from 2-phosphoglycerate. The high energy compound phosphoenol pyruvate is generated from 2-phosphoglycerate by the enzyme enolase. The high energy compound phosphoenol pyruvate phosphoenol pyruvate is generated from 2-phosphoenol glycerate. The high energy compound phosphoenol pyruvate is generated from 2-phosphoglycerate by the enzyme enolase. So now you will get phosphoenol pyruvate from phospho to phosphoglycerate by the enzyme enolase. It is a high energy compound. One more high energy we talked about, that is 1,3-bis phosphoglycerate. It is also a high energy compound. Another high energy compound is for phosphoenol pyruvate. This is by the enzyme enolase. So this enzyme requires magnesium and manganese. मन चाहिए, मन हाई एनर्जी फॉस्फेट बनाने के लिए, फॉस्फेट कंपाउंड बनाने के लिए फॉस्फोइनॉल पायरुवेट ना, इनॉल बनाने के लिए इनोलेस चाहिए. It is inhibited by the fluoride. So this is important. Which is inhibited by what? We talked about arsenate, which inhibits the dehydrogenase. Arsenate and iodoacetate. What is this iodoacetate and arsenate doing? They cause dehydrogenation reaction, that is phosphofructose, where we talked about dehydrogenase, where we were forming. So where we are forming 1,3-bis phosphoglycerate. Try to recall. See, the glyceraldehyde 3-phosphate was converting into 1,3-bis phosphoglycerate, where we were forming 1,3-BPG. We were using 3-phosphodehydrogenase. and for that iodoacetate and arsenate were the inhibitors, and here fluoride is the inhibitor. Here the fluoride is the inhibitor for enolase, and मन और मैगी चाहिए, मन चाहिए और मैगी चाहिए enolase. Okay. For blood glucose estimation in the laboratory, fluoride is added to the blood to prevent glycolysis by the cells. So what they do, they for glucose estimation they add the, because if the glycolysis takes place, then what happens? The glucose amount will reduce. That's why to inhibit it, fluoride is added, so that blood glucose is correctly estimated. Fluoride combines with magnesium and phosphate to form a complex that binds with the active site of enolase and blocks access to substrate. Thus, fluoride is an unusual competitive inhibitor. It is a competitive inhibitor. Today we talked about one more competitive inhibitor. What was that? Competitive inhibitor. Which competitive inhibitor we talked about? Decuferol. Decuferol it was. For vitamin K we were talking about, no? In vitamin K we have one decumarol, not ferrol, decumarol. It is a competitive inhibitor of vitamin K. And another competitive inhibitor is fluoride. The enzyme pyruvate kinase catalyzes the transfer of high energy phosphate from phosphoenol pyruvate to ADP, leading to the formation of ATP. This step is also known as substrate level phosphorylation. This reaction is irreversible. So again, the enzyme which is irreversible is phosphoenol pyruvate is converted to pyruvate. This is pyruvate kinase. Okay, pyruvate kinase, substrate level phosphorylation. This is irreversible. Okay, so this is about glycolysis. Now without saying, revise. So first, glucose is converted to glucose 6-phosphate. Glucose 6-phosphate is converted to fructose 6-phosphate. Fructose 6-phosphate, fructose 1,6-bisphosphate, fructose 1,6-bisphosphate to glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Then dihydroxyacetone phosphate to glyceraldehyde 3-phosphate, glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate, 1,3-bisphosphoglycerate to 3-phosphoglycerate, 3-phosphoglycerate to 2-phosphoglycerate, 2-phosphoglycerate to phosphoenol pyruvate, phosphoenol pyruvate to pyruvate. Now talking about enzymes. Glucose to glucose 6-phosphate by hexokinase or glucokinase, both are isoenzymes. Okay, both require magnesium and ATP. Now glucose 6-phosphate to fructose 6-phosphate by isomerase, that is phosphohexose isomerase. Then fructose 6-phosphate to fructose 1,6-bisphosphate by phosphofructokinase 1, phosphofructokinase 1, PFK1. And then fructose 1,6-bisphosphate to glyceraldehyde 3-phosphate and dihydroxyacetone phosphate by the enzyme we are breaking down, right? By aldolase and dihydroxyacetone phosphate to glyceraldehyde 3-phosphate by phosphotriose isomerase. Then glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate is by 1,3 glyceraldehyde 3-phosphate to phospho 1,3 bisphosphoglycerate dehydrogenase. Glyceraldehyde 3-phosphate dehydrogenase. Glyceraldehyde 3-phosphate dehydrogenase. Glyceraldehyde 3-phosphate dehydrogenase to 1,3-bisphosphoglycerate. 1,3-bisphosphoglycerate to 3-phosphoglycerate by 1,3-bisphosphoglycerate 3-phosphoglycerate by phosphoglycerate kinase. Then 2-phosphoglycerate Phos- then phosphoglycerate kinase 3-phosphoglycerate to 2-phosphoglycerate by phosphoglycerate mutase, and 2-phosphoglycerate to phosphoenol pyruvate enolase, phosphoenol pyruvate to pyruvate by pyruvate kinase, which is irreversible. The irreversible enzymes are glucokinase, hexokinase, and phosphofructokinase 1 and the pyruvate kinase. Inhibitors, talking about inhibitors, glyceraldehyde 3-phosphate dehydrogenase inhibitor is iodoacetate and arsenate and iodoacetate, and enolase inhibitor is fluoride. It is inhibited by fluoride. For glucose estimation, fluoride is added to get the correct estimation. Magnesium and manganese are required for enolase. So fluoride combines magnesium and phosphate to form a complex that binds with active site of enolase. And block access to substrate. Okay, this is all about. So NADH plus H plus is produced when glyceraldehyde 3-phosphate is converted to 1,3-bis phosphoglycerate, and 1,3-bis phosphate 3-phosphoglycerate ATP is produced first substrate level phosphorylation. Talking about the energetics. So if we talk about only 2 ATPs net are synthesized, 4 are synthesized, but 2 are utilized in the initial steps, no? So net is 2, and if you take by oxidative phosphorylation of NADH, then you will get 5 ATPs. The 5 plus 2, 7 you will get. In muscle you will get not by for glycolysis. Not for this. Okay. Okay. 2 minutes break. Okay, so let's talk about the further steps. So we talked about glycolysis. Now you remember, right, what are the enzymes and all that. So let's once revise the enzymes part. Okay, so glucose to glucose 6-phosphate by hexokinase glucokinase, and then glucose 6-phosphate to fructose 6-phosphate by phosphohexose isomerase, fructose 6-phosphate to fructose 1,6-bis phosphate by phosphofructose kinase, PFK1, and then fructose 1,6-bis phosphate to glyceraldehyde 3-phosphate and dihydroxyacetone phosphate by aldolase, fructose 1,6-bis phosphate aldolase, and then from dihydroxyacetone phosphate to glyceraldehyde 3-phosphate you required phosphotriose isomerase, and then G3P to 1,3-bis phosphoglycerate by G3P glyceraldehyde 3-phosphate dehydrogenase, and then from 1,3-bis phosphoglycerate to 3-phosphoglycerate by the enzyme phosphoglycerate kinase, and then 3 to 2 phosphoglycerate mutase, and then 2 to phosphoenol pyruvate enolase, phosphoenol pyruvate to pyruvate by pyruvate kinase, which is irreversible. PFK and pyruvate kinase and hexokinase or glucokinase are irreversible. Okay, so this is the enzyme and all. Once enzymes just glucose 6-phosphate hexokinase or glucokinase, and next hexokinase or glucokinase, phosphohexose isomerase, and then phosphofructokinase, and then aldolase, and then phosphotriose isomerase, and then glycerate 3-phosphate dehydrogenase, then phosphoglycerate kinase, phosphoglycerate mutase, then enolase, and then kinase, pyruvate kinase. So hexokinase or glucokinase, then phosphohexose isomerase, then phosphofructokinase 1, PFK1, and then phosphofructokinase 1, and then phosphofructokinase 1, and then aldolase, and then phosphotriose isomerase, and then G3P dehydrogenase, and then phosphoglycerate kinase, and phosphoglycerate mutase, enolase, pyruvate kinase. So this is the enzyme. Then now conversion to lactate. How it is converted to lactate? Under anaerobic conditions, lack of oxygen, pyruvate is reduced to NADH to lactate. Now you read for a next step of for the next cycle of glycolysis require NAD plus, right? So for that you need to regain the NADH. So pyruvate is reduced to NADH, reduced by NADH to lactate. Pyruvate is reduced to lactate. Pyruvate is reduced to lactate by NADH. In presence of the enzyme lactate dehydrogenase. Lactate dehydrogenase is the enzyme which uses NADH to reduce pyruvate to lactate. Lactate dehydrogenase. Competitive inhibitor of lactate dehydrogenase is oxamate. The NADH utilized in this step is obtained from the reaction. catalyzed by glyceraldehyde 3-phosphate dehydrogenase. And there you will get NADH. The formation of lactate allows the regeneration of NAD+, which can be used by glyceraldehyde 3-phosphate dehydrogenase, so the glycolysis proceeds even in the absence of oxygen to supply ATP. The occurrence of uninterrupted glycolysis is very essential in skeletal muscle. During strenuous exercise, your oxygen supply is very limited. Glycolysis is in the erythrocytes lead to lactate production. Since mitochondria, the centers for aerobic oxidation are absent. Brain, retina, skin, renal medulla, and gastrointestinal tract derive most of their energy from glycolysis. Brain, your retina, skin, so BR you remember glycolysis, renal medulla, GIT, all that. Lactic acidosis. Lactic acid is 3-carbon hydroxy acid. 3 carbons are there, it is an hydroxy acid. Elevation of lactic acid in circulation may occur due to increased production or decreased utilization. Normal lactic acid in blood in plasma is 4 to 15 milligram per deciliter. Mild forms of lactic acidosis, not life-threatening, are associated with strenuous exercise, shock, respiratory disease, cancer, thiamine deficiency, alcoholism, von Gilkes disease. Thiamine deficiency, alcoholics, cancers, respiratory disease, shock, strenuous exercise. Lactic acidosis. Severe forms of lactic acid observed due to impairment or collapse of circulatory system is often encountered in myocardial infarction, You can see lactic acidosis, pulmonary embolism, uncontrolled hemorrhage, and severe shock. This type of lactic acidosis is due to inadequate supply of oxygen. Inadequate supply of oxygen to the tissues with a drastic reduction in ATP synthesis, since the cells have to survive in anaerobic conditions which may even lead to death. The term oxygen depth refers to the excess amount of oxygen required to recover. In clinical practice, measurement of plasma lactic acid is useful. Measurement of plasma lactic acid is useful to know about the oxygen depth. Measurement of plasma lactic acid is useful to know about the oxygen depth and monitor the patient's recovery and save the patient from morbidity or mortality. You can monitor lactic acid. If plasma lactic acid raised, immediately give lots of oxygen, and then it is saved. Production of ATP in glycolysis. So the details of ATP generation in glycolysis and glucose, you can see the table. So under anaerobic conditions, 2 ATP are synthesized. Under anaerobic conditions, 2 ATP are synthesized, while under aerobic conditions, 7 ATP are synthesized if malate and shuttle pathway operates. Malate shuttle pathway operates. So when the glycolysis occurs from glycogen, one more ATP is generated. This is because no ATP is consumed for the activation of glucose. That is, glycogen directly produces glucose 1-phosphate which forms glucose 6-phosphate. Thus in anaerobic glycolysis 3 ATP are produced from glycogen. So which shuttle you require? Malate shuttle. मालामाल होने के लिए malate shuttle चाहिए. 7 ATP बनाना है, मालामाल होना है, malate shuttle चाहिए. So 3 ATP are produced from glycogen. So it is more advantageous than glucose. So if you take muscle, if you take liver, from there if glycogen is converted to glucose, then you will get 3 ATPs, because in glycogen it produces glucose 1-phosphate that can be converted to glucose 6-phosphate. No ATP is required for that, for conversion of glucose to glucose 6-phosphate. So one more ATP is generated, which is more advantageous than glucose. Glucose 6-phosphate and glucose 1-phosphate, more advantageous. Glycolysis and shuttle pathway. What is shuttle pathway? In presence of mitochondria and oxygen, the NADH produced in glycolysis can participate in shuttle pathway. If mitochondria is there, if oxygen is there, NADH produced in glycolysis can participate in shuttle pathway for the synthesis of ATP. If the cytosolic NADH uses malate shuttle pathway, 2.5 ATPs are generated from each molecule of NADH. This is in contrast to glycerophosphate shuttle, which produces 1.5 ATP. Refer chapter 11 if you will see in chapter 11. Shuttle pathway. PO ratio क्या है? PO ratio refers to the number of inorganic phosphate molecules utilized for ATP generation for every atom of oxygen consumed. For one atom of oxygen consumed, how many number of inorganic phosphate molecules utilized for ATP? Earlier NADH3 and FADH2 2, but now based on the belief that the two products protons were pumped at each complex 1, 3 and 4, resulting in the generation of 1 ATP, and thus that of total 3 ATP for NADH, like that they used to do. But studies, as per the recent evidence, the flow of 2 electrons from NADH and H+ through complexes 1, 3 and 4 results in the transportation of 10 protons. So 2 electrons results in the transportation of 10 protons from mitochondrial matrix. So the synthesis of 1 ATP requires the involvement of 4 protons. And there's a total of 2.5 ATP. 1 ATP, 4 protons. Then if 10 protons are there, how many ATP? 1 ATP requires 4 protons. 4 protons. Then 10 ATPs कितना होगा? 10 by 4, that is 2.5 ATPs. तो similarly 1 ATP के लिए 4 protons चाहिए. तो अगर सिर्फ तो 1.5 बनेगा for FADH2, because FADH2 will transfer 6, so 1.5. So it may be summarized that the oxidation of 1 NADH through ETC coupled with oxidative phosphorylation generates 2.5 ATP. Oxidation of 1 FADH2 yields 1.5 ATP. Coupling sites for NADH oxidation are 3 with 10 protons and FADH2 2 with 6 protons. सो शटल पाथवे के बारे में पीओ रेशियो कितना हुआ फिर NADH के लिए 2.5 और FADH2 के लिए 1.5, बिकॉज NADH के लिए 3 टाइम ऑक्सीडेशन हो रहा है एंड 10 प्रोटॉन्स जा रहे हैं. FADH2 के लिए 2 टाइम हो रहा है और 2 साइड्स है और 6 प्रोटॉन्स. ओके तो शटल देख लेते हैं एक बार. ट्रांसपोर्ट ऑफ रिड्यूसिंग इक्विवेलेंट शटल पाथवेज. तो यहाँ पे हमारे पास 3 शटल है. द इनर माइटोकॉन्ड्रियल मेम्ब्रेन इज इम्परमिएबल टू NADH. देयरफॉर द NADH produced in the cytosol cannot directly enter the mitochondria. 2 pathways, namely glycerol phosphate shuttle and malate aspartate shuttle, are operated through this job. They transport the reducing equivalents from cytosol to mitochondria and not vice versa. Only cytosol to mitochondria जा सकते हैं. Creatine phosphate shuttle is also there for high energy phosphate. Creatine phosphate. Okay, so let's talk about glycerol phosphate shuttle. So cytosolic glycerol 3-phosphate dehydrogenase. Glycerol 3-phosphate dehydrogenase oxidizes NADH2 NAD+. Glycerol 3-phosphate dehydrogenase oxidizes NADH2 NAD+. The reducing equivalents are transported through glycerol 3-phosphate into mitochondria. Glycerol 3-phosphate dehydrogenase present on outer surface of inner mitochondrial membrane. Outer surface of inner mitochondrial membrane reduces FAD to FADH2. Dihydroxyacetone phosphate escapes into the cytosol and the shuttling continues, and FADH2 gets oxidized via ETC to generate 1.5 ATP. Okay. So if you see glycerol phosphate shuttle, so here dihydroxyacetone phosphate is there. Cytosolic glycerol 3-phosphate dehydrogenase, it will convert into dihydroxyacetone phosphate, glycerol 3-phosphate. Glycerol 3-phosphate will enter the mitochondria, and here glycerol 3-phosphate in the mitochondrial matrix get converted to dihydroxyacetone phosphate by mitochondrial glycerol 3-phosphate dehydrogenase. And here the FAD produced is converted to FADH2. This way. Talking for glycerol phosphate shuttle is called FAD. Malate aspartate shuttle in the cytosol oxaloacetate accepts the reducing equivalents and becomes malate. Malate then enters mitochondria, where it is oxidized by mitochondrial malate dehydrogenase. So basically what happens here is in the cytosol oxaloacetate accepts the reducing equivalents and becomes malate. Malate then enters mitochondria, where it is oxidized by malate, mitochondrial malate. Dehydrogenase. In this reaction, NADH and oxaloacetate are degenerated. NADH get oxidized by electron transport chain and 2.5 ATPs are produced. In contrast to glycerol phosphate, where 1.5 ATP are produced from FADH2. So in mitochondria, oxaloacetate participates in transamination reaction with glutamate to produce aspartate and alpha-ketoglutarate. The aspartate enters the cytosol and transaminases with alpha-ketoglutarate to give oxaloacetate and glutamate. See what happens in the cytosol. Oxaloacetate accepts the reducing equivalence. What accepts? Oxaloacetate accepts the reducing equivalence, NADH, and becomes malate. Then malate, it enters the mitochondria, where it is oxidized by mitochondrial malate dehydrogenase to oxaloacetate. Now in this reaction, ADH and oxaloacetate are regenerated. See, oxaloacetate take NADH plus H plus and convert it to malate. Then malate goes into the mitochondria, then it will convert into oxaloacetate and releases the NADH. Now this NADH via electron transport chain, it will convert into 2.5 ATPs produced. So this is in contrast to glycerol phosphate, 1.5 ATPs are produced. In the mitochondria, oxaloacetate participates in transamination reaction with glutamate to produce aspartate and alpha-ketoglutarate. The aspartate enters the cytosol and transaminates with alpha-ketoglutarate. To give oxaloacetate back and glutamate. The malate aspartate shuttle, like this it will occur. तो जो साइटोसोल से माइटोकॉन्ड्रिया में जा रहा था वो वापस माइटोकॉन्ड्रिया से साइटोसोल में आना, लेकिन रेड्यूसिंग इक्विवेलेंट वो तो माइटोकॉन्ड्रिया में ही रहना. तो ऐसा हो रहा है, समझ रहे हो. टेक होम पॉइंट क्या है, डॉलर पॉइंट क्या है? पॉइंट ये है कि जो भी है ऑक्सैलोएसिटेट जो है या अपना डाइऑक्सीएसिटोन फॉस्फेट है, जो माइटोकॉन्ड्रिया में एंटर होगा, अपना रेड्यूसिंग इक्विवेलेंट एफएडी है, एनएडी है, वो निकालेगा माइटोकॉन्ड्रिया में, वापस जिस तरह से आया था तो वापस साइटोप्लाज्म में जाएगा माइटोकॉन्ड्रिया से. सो जैसे हम मैलेट एस्पेरेटेड शटल में देख रहे हैं कि जो हमारा क्या है ऑक्सैलोएसिटेट, उसने क्या किया, एनएडीएच लिया, मैलेट में बदल गया, माइटोकॉन्ड्रिया में गया मैलेट के फॉर्म में. ऑक्सैलोएसिटेट माइटोकॉन्ड्रिया में नहीं घुस सकता, मैलेट घुस सकता. मैलेट घुसने के बाद क्या किया, मैलेट डिहाइड्रोजनेस जो एंजाइम है, मैलेट डिहाइड्रोजनेस, उसने क्या किया, इसको ऑक्सैलोएसिटेट में कन्वर्ट किया, एनएडीएच बाहर माइटोकॉन्ड्रिया में आ गया, एनएडीएच जो 2.5 ATP बनाएगा. जो ऑक्सैलोएसिटेट है उसने ऑक्सैलोएसिटेट पार्टिसिपेट्स इन ट्रांसएमिनेशन रिएक्शन विद ग्लूटामेट के साथ बोला ट्रांसएमिनेशन करते हैं. ऑक्सैलोएसिटेट बदल गया एस्पेरेट में और ग्लूटामेट बन गया अल्फा कीटोग्लूटारेट. अब एस्पेरेट बन गया, एस्पेरेट निकला बाहर माइटोकॉन्ड्रिया के और ऑक्सैलोएसिटेट बन गया. फिर एस्पेरेट ने क्या किया, अल्फा कीटोग्लूटारेट से बोला चलो हम ट्रांसएमिनेशन करते हैं. फिर एस्पेरेट को बना दिया ऑक्सलेट और अल्फा कीटोग्लूटारेट बना दिया ग्लूटामिन. ओके, ये हो गया मैलेट एस्पेरेट शटल, जिसमें हम NADH बनाते हैं, NADH को ट्रांसपोर्ट करते हैं. ग्लिसरॉल फॉस्फेट शटल क्या करता है, बेसिकली ग्लिसरॉल फॉस्फेट शटल क्या करता है, ग्लिसरॉल फॉस्फेट शटल में जो ग्लिसरॉल 3-फॉस्फेट डिहाइड्रोजनेस है ना, जो मैलेट डिहाइड्रोजनेस मैलेट एस्पेरेट शटल में है ना, वो दो भी जगह है, साइटोसोल और माइटोकॉन्ड्रिया, और अमाइनो ट्रांसफरेज भी दो भी जगह है. अब ग्लिसरॉल फॉस्फेट शटल की बात करें तो ग्लिसरॉल फॉस्फेट शटल में जो ग्लिसरॉल 3-फॉस्फेट डिहाइड्रोजनेस है वो भी साइटोप्लाज्म में भी माइटोकॉन्ड्रिया में भी. माइटोकॉन्ड्रिया का अलग, माइटोकॉन्ड्रियल ग्लिसरॉल 3-फॉस्फेट डिहाइड्रोजनेज है, और साइटोसॉल का साइटोसॉल ग्लिसरॉल 3-फॉस्फेट डिहाइड्रोजनेज है। तो क्या होता है, जो रेडिसिंग इक्विवेलेंट है, जो ग्लिसरॉल 3-फॉस्फेट है वो घुसता माइटोकॉन्ड्रिया में, और वो बदल जाता डाइहाइड्रोक्सी एसीटोन फॉस्फेट में, और वहाँ पे निकालता अपना FADH। फिर वो वापस आता फिर ग्लिसरॉल 3-फॉस्फेट into mitochondria, glycerol 3-phosphate dehydrogenase outer surface of inner mitochondrial membrane reduces FAD to FADH2. Dihydroxyacetone phosphate escapes into cytosol and shuttling continues. फिर क्या होता, डाइहाइड्रोक्सीएसीटोन फॉस्फेट क्या करता, साइटोसॉल ग्लिसरॉल 3-फॉस्फेट डिहाइड्रोजनेज, फिर ग्लिसरॉल 3-फॉस्फेट। ओके, तो ये हुआ। क्रिएटिन फॉस्फेट शटल एक हाई एनर्जी कंपाउंड है। क्रिएटिन फॉस्फेट एक हाई एनर्जी कंपाउंड है। कौन? क्रिएटिन फॉस्फेट। क्लोजली लिंक्ड विद एनर्जी ट्रांसफर रिएक्शंस। क्रिएटिन फॉस्फेट शटल इन्वॉल्व्स ट्रांसफर ऑफ हाई एनर्जी फॉस्फेट फ्रॉम माइटोकॉन्ड्रिया। हाई एनर्जी फॉस्फेट फ्रॉम माइटोकॉन्ड्रिया। Creatine combines with ATP to form creatine phosphate into cytosol in the active tissue such as skeletal muscle and heart. This way, creatine phosphate shuttle functions as an energy buffer to transfer a high energy phosphate and generation of ATP in the extramitochondrial system generation of ATP. So creatine combines with the phosphate to form creatine phosphate in skeletal muscle and heart. Mitochondrial isoenzyme of creatine kinase. In addition to the 3 cytosolic isoenzymes of creatine kinase, BB brain, MB muscle and brain, MM muscle. So 2 mitochondrial creatine kinase, that is mitochondrial creatine kinase, have been identified, ubiquitous, and they are ubiquitous and sarcomeric. Both mitochondrial creatine kinase are octamers consisting of 4 dimers each. But cytokinase are directly involved in the formation of phosphocreatine from mitochondrial ATP, participating in creatine phosphate shuttle. Shuttle pathways in tissues. Liver and heart utilize smallly transported shuttle. इनको एनर्जी ज़्यादा चाहिए, 2.5 ATP per mole of NADH. Other tissues employ glycerol phosphate shuttle and liberate 1.5 ATP from NADH. Creatine phosphate shuttle is active in skeletal muscle and heart. skeletal muscle and heart, creatine phosphate shuttle. ठीक है, एक बार हम इनहिबिटर्स एंड अनकपलर्स पे ध्यान डालते हैं। तो इनहिबिटर्स ऑफ ऑक्सीडेटिव फॉस्फोरिलेशन, अनकपलर्स और इनहिबिटर्स देखते हैं। माइटोकॉन्ड्रियल ट्रांसपोर्ट ऑफ इलेक्ट्रॉन इज टाइटली कपल्ड विद ऑक्सीडेटिव फॉस्फोरिलेशन, ATP synthesis. So in other words, oxidation and phosphorylation proceed simultaneously. There are certain compounds that can uncouple or delink. That is, uncouple the oxidation and phosphorylation. The electron transfers from oxidative. So they can uncouple the electron transport chain from oxidative phosphorylation. Such compounds are known as uncouplers. So they increase the permeability of inner mitochondrial membrane to protons. The result is that ATP does not occur. The energy linked with the transport of electrons is dissipated as heat. The uncouplers allow often accelerate rate oxidation of substrate via NADH or FADH2 without ATP formation. Uncouplers allow oxidation of substrates without ATP formation. The uncouplers are DNP, 2,4-dinitrophenol. It is extensively studied. It is a small lipophilic molecule. DNP is a proton carrier and can easily diffuse through the inner mitochondrial membrane. It can take proton and diffuse easily from inner mitochondrial membrane. In the people seeking to lose weight, DNP was used as a drug. However, this is now discontinued. as it produces hyperthermia and other side effects. Hyperthermia, fever. In fact, the Food and Drug Administration USA has banned DNP. The other uncouplers include dinitrocresol, pentachlorophenol, and trifluorocarbonyl cyanide, and phenylhydrazone (FCCP). The last compound FCC is said to be 100 times more effective as uncoupler than dinitrophenol. When administered in high doses, the drug aspirin acts as an uncoupler. Aspirin also acts as uncoupler when taken in high doses. Physiological uncouplers. Certain physiological substances which act as uncouplers at high concentration have been identified. They include physiological homogenein thyroxine, long chain free fatty acid, unconjugated bilirubin, so what are uncouplers? DNP. DNP is an uncoupler. 2,4-dinitrophenol. DNP is an uncoupler. It is a lipophilic. It is small and lipophilic, and it can easily take proton carrier, and it can easily diffuse to the endomitochondrial membrane. That is FCCP, trifluorocarbonyl cyanide phenylhydrazone. FCCP. It is 100 times more effective uncoupler than dinitrophenol, and when aspirin is taken in high doses, it also works as uncoupler. Another is dinitrocresol, dinitrophenol, dinitrocresol, and pentachlorophenol, and FCCP, trifluorocarbonyl cyanide phenylhydrazone. These act as uncoupler. What they do, they easily diffuse through the inner mitochondrial membrane, and they disturb the proton distribution, and they increase the permeability of inner mitochondrial membrane to protons. So ATP synthesis does not occur. And heat is produced. What they uncouple? They uncouple ETC with oxidative phosphorylation. Okay. This is the things you need to remember. So what are the inhibitors of electron transport chain? So NADH and coenzyme, fish poison, rotenone, barbiturate drug, amital, and antibiotic pyrisidine A inhibit this side. So inhibitor of NADH and coenzyme Q is amital, barbiturate drug. Between cytochrome B and C1, antimycin A is an antibiotic, and BUL, British anti-Lewisite. Yesterday we have seen this, British anti-Lewisite. Cytochrome B and C1, antimycin A, and BUL. So this is an antigas for VAR gas. But what they do, they inhibit the electron transport chain also. They act as antidote for VAR gas, but they also inhibit cytochrome B and C1. Inhibitors of cytochrome oxidase. Cytochrome oxidase का carbon monoxide, cyanide and azide. Carbon monoxide react with reduced form of cytochrome, and cyanide and azide with oxidized form of cytochrome. Cyanide is probably the most potent inhibitor of ETC, and it binds to Fe plus 3 of cytochrome oxidase, blocking mitochondrial respiration, leading to cell death. Cyanide poisoning causes death due to tissue asphyxia, especially of central nervous system. Cyanide is a popular suicidal agent commonly used by militant terrorists and warriors. Cyanide containing compounds include hydrogen cyanide gas H2, hydrogen cyanide hydrogen cyanide gas, and certain cyanide salts, potassium cyanide. If cyanide is inhaled, it causes coma, seizures, cardiac arrest, finally death in a few seconds. At lower doses, cyanide causes headache, weakness, giddiness, confusion, difficulty in breathing. Treatment of cyanide poisoning, especially designed antidote kits, are available. The kits usually contain amyl nitrate and sodium nitrate. The nitrate converts hemoglobin into methemoglobin. Hemoglobin to methemoglobin. Hemoglobin to methemoglobin. Cyanide binds to methemoglobin, forming cyanomethemoglobin. This results in the release of cyanide from cytochrome oxidase. Recent years, hydroxycobalamin, a form of vitamin B12, is used as an antidote for cyanide poisoning. The reaction involves the conversion of cyanide to harmless cyanocobalamin. So, hydroxycobalamin is also given vitamin B12. So, this is all about. So we'll be discussing about glycogen and all next video. Thank you.